In this video, we'll learn about neural networks. First, we'll learn about what is an artificial neuron. Artificial neurons function similar to a biological neuron and it is referred to as a node. A node or neuron can receive one or more inputs and process them. These nodes are interconnected through links, with each link having an associated weight. Consider this example. Here, x1 is an input, it has an associated weight w1. x2 is an input, it has an associated weight w2, and so on. And this is the particular node. Each node will be interconnected with a link. Now we'll learn about the mathematical model of an artificial neuron. The first mathematical model of a biological neuron was designed by Meckel and Pitts in 1943. You can see here, this is the mathematical model of an artificial neuron. Here you can see the inputs as x1, x2, x3, etc. to xn, and the weights as w1, w2, w3, etc. to w1. What the node will do? Here the summation function will happen. What is the summation function? It just does x1 into w1 plus x2 into w2 plus x3 into w3 plus etc. to xn into wn. This output is said to be the net sum. This net sum will be given to the activation function. In this case, the activation function is the binary step function. And after this activation function, it produces an output y. Now we learn about the activation function, which is the binary step function. The activation function takes the input as the net sum. Already we have seen what is the net sum, which is summation of I xi into wi. That is the net sum. The output will be taken here in the activation function. If the activation function f of x is greater than or equal to the threshold theta, then the output will be 1. If the activation function f of x is less than theta, the threshold, then it produces the output 0. So this is the mathematical model of an artificial neuron. So when you consider this artificial neuron, it can represent only few Boolean functions. A Boolean function will have binary input and provides a binary output. For example, when you consider an AND Boolean function, it would fire when all the inputs are 1. The weight and the threshold values won't be changed in the mathematical model. Now we'll learn about the artificial neural network structure. ANN structure. So this shows the structure of the ANN. Now we'll learn about artificial neural network structure. That is the structure of ANN. The ANN imitates a human brain which inhibits some intelligence. Actually, it has a network structure which is represented as a directed graph with a set of neuron nodes and connected links or edges connecting the nodes. So you can see here, these are all the nodes. And these nodes are connected through the connecting links. You can see here, these are all the connecting links. The nodes in the graph are arranged in a layered manner and can process information in parallel. The network in this figure, here it shows it has 3 layers: input layer, hidden layer and output layer. When you consider the input layer, the inputs are x1, x2, x3, etc. to xn. The edges connecting the nodes from the input layer to the hidden layer are associated with weights called as connecting weights. For example, this node employs an activation function that determines the output of this particular neuron. The neuron transforms linearly the input signals by computing the sum of the product of input signals and weights and adds bias to it. Then the activation function maps the weighted input sum to a non-linear output value. The node in the output layer gives the output as a single value. This is all about artificial neural network. Now we'll look into the activation function. What are all the activation functions which can be used in the neural network? Activation functions are the mathematical functions associated with each neuron. It decides whether to fire a neuron or not based on the input signals the neuron receives. These functions normalize the output value of each neuron either between 0 or 1 or between -1 and +1. Typical activation functions can be linear or non-linear. We'll see about the linear functions and non-linear functions. Linear functions are useful when the input values can be classified into any one of the two groups, and are generally used in binary perceptrons. When you consider about non-linear functions, these functions are useful in learning high-dimensional data or complex data such as audio, video, and images. We'll see about the different types of activation function. The first type of activation function is identity function or linear function. It is represented as f of x is equal to x for all x. So how the graph looks like? Here this is the 0 point, and this is the x-axis, and this is the y-axis. So it represents as f of x is equal to x. It means that it represents the x value as such. So the graph goes this way. It means that the value of x increases linearly or proportionally with the value of x. This function is useful when we do not want to apply any other threshold. Here the output value ranges between -infinity to +infinity. The next activation function we are going to see is binary step function. So how we'll represent this binary step function? F of x is equal to 1 if f of x greater than or equal to theta, 0 if f of x is less than theta. So it means that the output value is binary value. Either it can be 0 or 1. It's based on the threshold value theta. So here this shows the step function. This is the x-axis and this is the y-axis. It can be either 0 value or it can be 1 value. So directly it steps up from the 0, it directly steps up to 1. So that's why it is said to be binary step function. Now we'll learn about bipolar step function. In bipolar step function, the mathematical representation is as f of x is equal to 1 if f of x greater than or equal to theta, -1 if f of x less than theta. The output value is bipolar, that is +1 or -1. It's based on the threshold value theta. So here it can be -1 or it can be +1. The next activation function is sigmoidal function or logistic function. It is mathematically represented as sigma of x is equal to 1 divided by 1 plus e power minus x. This is the widely used nonlinear activation function which produces an S-shaped curve, and the output values are in the range of 0 to 1. It has a vanishing gradient problem. It means that no change in the prediction for very low input values and very high input values. The next one is bipolar sigmoid function. It is represented as sigmoid of x is equal to 1 minus e power minus x divided by 1 plus e power minus x. Here the output values between -1 and plus 1. Here you can see the S-shaped curve which lies between minus 1 and plus 1. The next one is the ramp function or step function. So its mathematical representation is as f of x is equal to 1 if x greater than 1. Otherwise, x if x lies between 0 and 1. Otherwise, 0 if x is less than 0. So, if x is less than 0, it lies in 0th position itself, and if x lies between 0 to 1, it's like a slope, and then if x is greater than 1, it stays in 1 itself, it outputs 1 itself. So this is like a ramp, and so this activation function is said to be a ramp or step function. The next one is tan h or hyperbolic tangent function. It is represented as tan h of x is equal to 2 divided by 1 plus e power minus 2x minus 1. The representation of tan h is a S-shaped curve. This tan h function is a scaled version of the sigmoid function, and this is also a non-linear function. It also suffers from the vanishing gradient problem. Here, the output value ranges between minus 1 to plus 1. Now we will look into what is the difference between sigmoid as well as tan h. Both are S-shaped curve. Even though both are S-shaped curve, sigmoid looks this way, and tan h is a properly S-shaped curve which ranges between minus 1 to plus 1, whereas the sigmoid is from 0 to plus 1. We now will see about the difference between bipolar sigmoid or as well tan h function. In bipolar sigmoid, you can see it's like an S-shaped. Even though it's an S-shaped, it's not a proper S-shaped, whereas in hyperbolic tangent, you can see the difference between the bipolar sigmoid and hyperbolic tangent by looking into the diagram itself. The next activation function is ReLU, which is rectified linear unit function. It is mathematically represented as R of x is equal to maximum of 0 comma x, which is equal to x if x is greater than or equal to 0, 0 if x is less than 0. So the diagram of our ReLU looks this way. This activation function is generally used in deep learning neural network models in most of the hidden layers. This reduces the vanishing gradient problem. This function outputs a value of 0 for negative input values, and it ranges between 0 to x. The next one is softmax function. It is mathematically represented as S of xi equal to e power xi divided by summation of j equals to 0 to k e power xj, where I is equal to 0 to k. This is a nonlinear function, and it is used in the output layer, which can handle multiple classes. This calculates the probability of each target class, which ranges between 0 and 1. The probability of the input belonging to a particular class is computed by dividing the exponential of the given input value by the sum of the exponential values of all the inputs. Thank you.